Now, these preliminary images, and I call them preliminary because all sorts of defects are in them that we will remove when we process our own data. So the last thing I want to do is go through the defects that you might see. The first one is this zigzag. See how the source is zigzagged? They're not really zigzagged. It should just be kind of a Gaussian blur. What's going on here? Okay, best I can tell. We're still trying to figure out exactly what's going on, but here's what I think is going on. We're reading two things. As the telescope's moving along, we're reading the flux, the intensity, and we're reading the position of the telescope. And these are getting out of sync. We're getting the fluxes shifted in time with the positions. So they're either ahead of the position or behind the position. So when we plot them, they're in one direction or the other. Then when the telescope turns around, it's the same shift, but in the other way. The telescope turns around again, same shift, but back to the original way. So there's some kind of time delay between the recording of the flux and the recording of the position. And in our fancy algorithm in the next video, it can correct that as long as the source is bright enough. As long as it's bright enough, we can grab enough information from the data to figure out what that time shift is and correct it. Now, sometimes the source might not be bright enough. Jupiter is a really, really faint source. You can just barely see it here. It looks really bad in the preliminary image, but you'll see once we make our own images and correct for all the defects, it can be quite good. But there has to be enough flux in here, enough signal to latch on and figure out what the time shift is. That's not always the case with Jupiter. So you may end up having to do Jupiter twice. We'll talk about that in upcoming videos. If there's not enough there to get a good time shift measurement, you may have to play with it. But for the moon, the calibration sources should be easy. We can measure the time shift. What else can go wrong? Let's go to this paper. This paper is referenced in the module. This is the paper where we describe our algorithm for making the final images. And let's look at a few figures here. Let's start with this figure on the left. This is a big map. This is 30 degrees by 30 degrees. The map we were just looking at around the source is, they're only 4 degrees by 4 degrees. And this is 30 degrees by 30. So it's a big map, a big chunk of the sky. A lot of data, took a lot of time to collect. That's Virgo A, same as this source right here. This is quasar 3C273, one of the closest quasars to us. It may be hard to see with the color scaling, but it won't be after we make our final images. Or we're not going to do this one, but once you turn this into a final image, it comes out very easily. There's another source right there. It's another galaxy, a supermassive black hole in the core of a galaxy, gobbling up some gas. Now, there are 3 defects you can see in this image. The first one, the most subtle one, is called the scanning effect. And I'm actually not sure how well, I'm just doing this over Zoom, and so I'm not sure how well you'll be able to see it over Zoom. But when I look at this, I see horizontal streaks. And it's just telling me that's how I mapped. I mapped this one left, right, horizontal. And as the telescope was moving, conditions changed for a couple reasons. One is called spillover. So here's a radio telescope. This is a different one, but the picture's here. We have the dish, we have the receiver. Normally the rays come in from space, bounce off the dish, go into the receiver, where it's detected by those 2 beams, those 2 metal bars. Think of it backwards. Think of it from the receiver. The receiver is looking out at the dish that's looking up into space. And it's not perfect. There's no sharp edge to that, the receiver looking out to the dish. These are waves There's never a sharp edge when you're dealing with waves. And so it actually has some sensitivity over the lip of the telescope. We try to under illuminate these so you don't have much of that. But if the dish is a little bit over illuminated, some of the sensitivity is over the edge. And that goes on and intersects the Earth. So as I move the telescope around, I'm getting Earth background. In fact, these sources are actually quite faint compared to the background level. It's a background dominated data set. That background is all emission from the Earth. And as I go back and forth and change how the receiver is oriented towards the ground, I get different amounts of Earth radiation. And so it varies, it's changing as it goes. There's another effect. Let me pull it up here. So it's kind of interesting. It's noise in electronic systems. When we normally think of noise, we think of white noise. You can see it here. Each point is not related to the point before or the point after. White noise. Some people listen to white noise because it helps them sleep. This is called brown noise. It drifts. It doesn't remember where it started. It's kind of walking around randomly, but it can wander away. Brownian motion. You may have heard of Brownian motion. It wanders away, called brown noise. Many electronic systems produce pink noise. The noise is correlated. It does remember the noise from before, and it will affect the noise in the next read. But it doesn't wander away. It maintains the same level, but there's kind of correlation. Each point isn't independent. It drifts around. It doesn't drift away, but it drifts around. And this is called pink noise. And they have different spectra, but we won't get into that. Electronics, being pink noise, it's drifting around. So as the telescope's moving, that background level is drifting around because of that pink electronic noise. In addition to the over illumination of the lip of the dish, getting different Earth radiation. So you put all that together, you get the scanning effect. You get this effect where you can see the scans, and you don't want that. You want your image to look like a picture, not like something that ran through a bad fax machine. Only the older viewers of this video will understand that. Okay. What else is wrong with this image? RFI, radio frequency interference. That's the primary thing. As we're going back and forth, right at this time, something started transmitting in our frequency range, got quite bright here. Here it turned around, it's still bright, and continued to kind of the end, and then it kind of stopped. So most of it's only one scan thick, some of it's two scans thick, two scans, two sweeps, whatever you want to call it. And it's clearly RFI because all astronomical sources are blurred out the same amount by the optics of the telescope. That's astronomical, that's astronomical. This thing that you can barely see is astronomical, blurred out in all directions. This is really skinny in one direction and too long in the other. The fact that it's really skinny in one direction, just along the scan, tells us this isn't from space. This is something that's getting into the receiver as a function of time. It's RFI, radio frequency interference. There's some more up here. Here's just a little blip, and here's a little blip. Sometimes it turns on and stays on for a while. Sometimes it's just a snap of radio interference. And our algorithm will help us to remove this. The last thing is, as this map was being taken, it took a while to take, and the field was getting ready to set. And so as it was getting back into this final corner up here, that was actually getting pretty close to the ground. The ground emits radio waves. In fact, most of what we're seeing is the background. The background is the dominant source here. And here we're getting close to the ground. And so we're starting to pick up Earth background just by looking at it directly, not leaking in over the lip of the telescope, but from the front of the telescope, because we're pointing close to the horizon. This thing ended 11 degrees above the horizon. You kind of want to stay above 15 or 20, or you'll start to pick it up. Because this place and many radio observatories are in valleys. They use the surrounding mountains to block RFI. A lot of RFI is coming from the ground. If you're surrounded by mountains, that can protect you. But if you point the telescope down at the mountains, you'll detect the mountains. Okay, so the four problems were time delay problem, the scanning effect, RFI, and elevation dependent background. Okay, in the next video, we're going to learn how to get rid of all of this and make a gorgeous picture of something that you can't see with your